Welcome back, guys. I had a deep feeling of unwellness inside me, deep inside me, that was bothering me. In one of my last videos, the one about patching a file on assembly level, many of you in the comments freaked out, telling me what I was misunderstanding about assembly and telling me that I am a noob. And that's totally fair. So I sat down, read through your comments, and really tried to study them. And as you can see, there's some leftovers from my study session where I practiced understanding of assembly instructions, and I decided I want to test my improved knowledge now using an assembler crackme. So this is a crackme that was written in pure assembler, and we're going to try to reverse engineer it and try to find the password. Or I don't know what we have to do there. I haven't tested it yet. And also for studying, I read The Faker's Guide to Reading x86 Assembly by Tim Debug. It's a nice little guide. I found it very useful for, well, reading assembly language, for which gave me a bit of insights that might help me in this episode. So I read through that. Of course, it doesn't go into assembly too deeply, but it made me understand at least the syntax of instructions roughly. So yeah, as always, we're constantly improving. Let's jump right into the crackme itself. It's written in assembler, and I picked it out because it has a difficulty of 1.0, so it's perfect as the very first crackme that is a pure assembler crackme. So let's get it. Before we get it, of course, I have to delete all the directory contents here and download the new crackme. Let's go. And there it is. It's called NASM crack. I don't know what NASM stands for, but we're going to crack that one today. I'm going to persevere until it's cracked, regardless of how bad I am at assembler. No, I'm not bad at assembler. I am going to be the master of assembler very soon by constantly improving myself here. With your help, of course. So let's run the application and see what happens. It prompts us to enter the password, and let's just try something. Password, and it tells us wrong. Can we enter a password via command line argument? No, we can't. Wrong, but we can probably pipe it in. Let's just test this. Yes, that also works. So technically we could even use a brute force as we did in the last episode, but I don't know if that password is a difficult one to retrieve. Now, I don't want to use strings and then call this, because if the password is embedded in the crackme in clear text, which is quite likely because it's a simple crackme, then we already know the password. Let's do it. Let's see. Super secret. Oh god. NASM crack, super secret. No, super secret is the standard input, and it's correct. So that is the password. How do we crack it? We can call, so that one was easy to crack because of the strings utility, which also you pointed me at. But we can use object dump s super NASM crack to, oh, that's a small file. Object dump d NASM crack to read through that stuff here. Let's see. As you can see, there's a start section and a correct func section. And now by reading just the disassembly, what can we learn? Let me also enable the Intel syntax on object dump help And right, using -m Intel, we can enable Intel syntax, which is a bit nicer to read. But in the end, it doesn't make a big difference. It's still the same code. All right, so looking just at this, how are we supposed to find out that the password is super secret? Oh, super secret. How are we supposed to do that? Well, we could start by looking at the start function here. And there's a jump if equal instruction, which jumps to the correct function, whatever that means. Jumps are always suspicious for crackmes because they usually follow a check. Reps compares byte pointer ds RSI byte pointer ES RDI. That looks like a comparison that compares values, and that's probably the instruction that contains the super secret thing, the super secret password. But how reps? I'm going to look up that instruction now. Reps. Assembly. Repeat string operation. Repeat while equal, repeat while 0. It's a repeat while 0 operation. So it's a string comparison operation that transfers the contents of the EAX register to the memory double word address in the designation register EDL relative to the ES segment. Okay, I understood close to nothing. Transfer the contents of the EAX register to the memory double word address in the destination register EDL relative to the ES segment. Reps CMPS. Reps CMPS. Repeats a string instruction the number of times specified in the count register. What's the count register? Assembly count register is ECX. And here a value is written into ECX, and that value is B. And B, by coincidence, is probably the length of the password. Because B is hexadecimal for, is it 11 or 12? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B. It's a 12. No, it's an 11. A is 10, B is 11. And super secret, the password is also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, okay, that's already something good to know. Now, the length 11 is moved into ECX. The count register, also something new that we just learned. Then reps executes this comparison ECX times, so 11 times, and it compares the byte pointer. I don't know why there is the specification of this data type here. DS, RSI, and ESRDI. RSI, and RSI is also referenced here, move apps, and then something is written into RSI, and this is written into RSI. So is this already the string? And this? And what about this? Compare. And the correct function is the function that prints out that the provided password is correct. And here different values are written into registers. And then there's a syscall. Well, what does it call? Syscall. Syscall. The syscall is probably referencing or calling some function according to some value written here. Assembly syscall. Actually, we don't need to even know this, because we know that this is the printout of the success message, so we don't even further need to reverse engineer it. I was just curious how the system call knows what to do. System calls are the interface between user programs in the Linux kernel. They are used to let the kernel perform various system tasks, such as file access, process management, and networking. Okay. On Linux, there are several ways to make a system call. This page will focus on making system calls by calling a software interrupt using int something or syscall. I would expect it to take an argument. Okay. You specify the system call by writing the number into the EAX/RAX register. And the guy from WinDebug here in the guide, the Faker's Guide to Assembly, he wrote that EAX is a register that is the low 32 bits of the RAX register. So that's why here, well, I skipped the position in the text somehow. EAX. Yes, that's why here EAX and RAX are used interchangeably. Most system calls take parameters to perform their task. Those parameters are passed by writing them in the appropriate registers before making the actual call. Each parameter index has a specific register. Okay, so probably here registers are written and filled with values to perform the system call, and once all registers are populated, the system call is performed here. Interesting. Which system call is executed here? I would expect something that prints to the console, and it must be system call 1. Do I understand this correctly? And then there's maybe this is what is this? What is system call 1? How do we know which system call number represents what? I know that from this Faker's Guide, this guy also somewhere mentioned system calls there. And system calls are also used for breakpoints, but here they are always integer 3. What is int again? It's for the int instruction, which stands for int. Oh no, it's not integer, it's interrupt. And it's used to trigger a software interrupt which will switch the CPU into kernel mode. Blah 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 blah. Okay. And this has been frequently replaced by the syscall, sysenter instructions because they are better suited for calling stuff in the system. All right. But now how do we get from moving just some stuff into registers to writing some message into to standard out? Where is that message coming from? Okay, I have an idea. Probably this move apps RSI. This is probably the register that takes a memory location, because this looks very much like the strings over here. So 402016 refers to a memory location, and 402116 is specified down. Where is it? It's not there. (402.016), and it's not accessible from inside here. Maybe it is not part of the object dump of the disassembly because it's outside of the memory range that can be disassembled. So let's dump all sections and try to dump all the contents of that file. And as you can see, that memory location in the disassembly, referenced here in the disassembly, 402016 refers to 40201, and then 1, 2, 3, 4, 5, 6, and then it's the string starting with this 436F 7272 blah blah blah, and it's exactly this correct string. It's 402016, so it's the string starting at the 6th character here. 0, 1, 2, 3, 4, 5, and then 6. Correct. And then this dot is probably a 0 terminating character. It's just a 0 byte. Let's check here. 1, 2, 3, 4, 5, 6. No. CORRECT exclamation mark and then a 0. It's just it's just half a byte of a 0, but it seems to be enough for the 0 termination. It's a 0A. All right, but probably that's how 0 termination somehow works. Yeah, I'll just accept it. And then, now this disassembly gets even easier. So something is written into this memory this memory location is written into this register, then a syscall is performed, and the syscall is probably somehow writing something to the console. Because the registers are set in a way that something is written to the console. And then There's another syscall here, which I don't know what it's doing. I think because this is the correct function, it's the function that prints out the string that the password attempt is correct, that the correct password has been provided. But I don't know why there are two syscalls here. If you know it, put it in the comments. This is definitely an important point to find out about. So this is also setting some value into EAX, and EAX is probably, since it's also set here with this syscall, I suspect that this is somehow defining which syscall is going to follow. Let's check assembly syscall table. Maybe that's what we need. Linux system call table for x86-64. I would expect some table that contains the codes. Oh, yes, there is. Aha, okay. So here, this is the system call 0x1. So it's just a 1. And it's system reading. Ah, no, it's system writing. It's writing something. It's writing something, and these registers here are the input parameters. This is the file descriptor, so it can be standard out, standard error, or some file descriptor that is opened. That's awesome. I feel like I'm learning something. This is really awesome. Then we have this constant character buffer here, which is probably what is written to this is written to the file descriptor, but this is written into this is specified in RSI. RSI is here, which is the memory location, which we just checked, which is the string correct. And then there's this RDX register, which is the size T count. And this is not set. Probably I don't know if it's not necessary, but it's certainly a string that is terminated, so maybe it's not necessary. I don't know. I mean, the assembly code is working, so probably it's not necessary. I can see in the code that the RDX is not set here, so I'll just assume that it works like this. Or alternatively, RDX or EDX is probably a variable within RDX, just like EAX is within RAX. So probably that's writing to RDX and specifying that it's a string of length 9. So we don't even need a 0 terminator at the end of the string. Okay. That's awesome. And the string correct exclamation mark, is it 9 characters in length? CORRECT exclamation mark. And then there's one more 0 in the memory. And the 0 is just right, it's almost 9. It's actually 8 real ASCII characters, and then the last thing is probably the terminator. Maybe it's a new line character. Is it a new line? Man ASCII. Let's check. Backspace N. Wait, what did we see in memory here? It's the value 0A. Let's check the value 0A here. And yes, it's the new line. Okay, so we have perfectly understood now why the instructions in the disassembly are the way they are for this section here. And now the next part would be calling another syscall here, and the syscall that is being called is this one, 0x3c. And 0x3c is, what is it? 0x3c. is 60. Okay, so that's the code 60. Let's look it up in this syscall table. It's sysexit. Aha, okay. So this exits the function and sets an error code in the register RDI. And that's it. And EDI is a sub. Well, is it a substring, a subvariable? What I always think of in my head is that is this thing right here. It's just, I imagine this to be RDI, and then the lower bits are EDI. And I always imagine this. I imagined this for the last, let's say, 1 hour since I started learning about it. All right. Don't save this and go. Okay, so this is printing correct to the console, and this is exiting the function. Oh, this is, yes, sending a syscall exit that probably exits the printout. Well, it exits something. Yeah. And then there's the return, which pops the call which was done. Where's the success message done? It's probably here. Ah, yes. So this is the jump. If the strings are equal, then we jump to the correct function. This is the memory location of the correct function, which is this right here, or this. And then the return function up here just returns the instruction pointer's value to, I think, this. Or this. One of those. So basically the execution just returns to where it came from. All right. That's quite fun. I am enjoying this a lot. And I'm just curious where the password is stored. I mean, we have already found it in memory. I'm just curious where it's coming from. And probably we should have a look at the start and how the method even starts overall. So again, we move something into EAX 0x1, and as we know, it's write. This is the write system call. Then EDI is the, oh god. This is the file descriptor standard out, of course. Yes, this is standard out. So we say we want to write something, we want to write to standard out, and then we say we want to write this message here to standard out. And this message, let's have a look what it is. 402.000. 402.000. It's right here at the beginning of the data section, and it's enter your password, space. Perfect. So this is printing out. This is awesome. This is so much fun. I love it. I really love it. This makes my hacker's heart glow up in pure enjoyment, really. Especially because for the last even years, I've always had in the back of my mind that assembly is some magic thing that only the most advanced minds can ever comprehend. But I mean, maybe writing it is hard, but we can actually understand it by reading it. It's awesome. And I mean, I'm not alone trying to read something unreadable here. I have Google at my hands. I have the man pages at my hands. And like this, we can proceed step by step and have some fun. It's awesome. All right. So this code is writing something to standard out then moving into RSI the memory location of what is to be written to standard out, and then it's specifying that the length of what is to be written is 0x16, which is 0x16 is 22. So this is a string of length 22, which makes sense because enter your password has the length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, including the space. Okay. Now, next step. The next step. So we are printing a string to the console here, doing the system call. Then there's another system call down here. Before we do that, we write into EAX 0, into EDI also 0. That means we want to, we specify that we want to read something, if I remember correctly, because the 0th system call is system read. System read, and where do we want to read from? We want to read from standard input, which is file descriptor 0, which we also learned in some recent episode. I think we talked a lot about file descriptors in the episode on bash redirections. So in case you want to learn more about those, then you can have a look there. Very interesting how to deal with the file descriptors, how to redirect them. And also just hammer in your head that 0 is standard in, 1 is standard out, and 2 is standard error. And everything else, 3, 4, 5, 6, are files that you can create yourselves. All right. And then we are reading something from standard in, and then we specify another memory location, but what is it used for? We read something from that's the memory location that we want to read into, and we want to read into 16 characters. 0x10 should be 16 characters, right? Yes. Okay, and then that's going to be then a syscall is performed with all these registers set, and the user is prompted to enter a password. So let's try. This is the first system call. It's writing something to standard out, and then now the second system call is already being performed, waiting for the user to write something into standard input. So let's try that, and it's wrong. And if we echo something and pipe it via standard input into that, then the application doesn't need to block and wait for user input because standard input is already coming from this echo statement. Okay. So this is the second system call. All right. Now, the user has entered something, and the value, where is it written? It's written into this memory location, I think. And what is that memory location? It's 402031. And is that... I'm confused because I would expect this to read into some memory location either on the stack or the heap. I don't know if these concepts even exist like that in pure assembler. But this reads into a memory location, and that memory location is obviously beyond the program's instructions range. And okay. So this is reading into 402031. No, sorry. It's reading into 402.031. Okay, that was correct. So this is the memory location. Remember it, 402.031. And if we check out the dump of all the memory segments, then you can see that the last address is 402.030. So the reading of the data from the user happens right after the fixed program's memory location. So all of this is the program's memory, and the space after that is written or is used for reading stuff from the user. So reading stuff happens outside the program, of course, and that makes sense. That is the assembly code. I'm just not sure how much and what the difference during runtime is, because during runtime that is not going to be the correct address. I think this is just going to point to one after the program in memory, and the memory location during runtime is not going to be this. This is just the memory location right now on the disk, basically. Well, not even that. I don't know. What is this relative to? It's not the absolute memory location on the disk. It's some relative memory location, I don't know, for the disassembly. Anyways, okay. So the user is reading something into this memory location beyond the program running in memory. And then there's another syscall. No, there's not. This is the syscall. And this is specifying that it's reading up to 16 characters. And then something else is happening here and here. There are two move statements and yet another move statement. There's a difference between the move apps and the moves, probably, but I don't think it's relevant for now. Or is it? Move apps is probably ignoring the sign before the value. But this is unsigned anyways. I don't know. What's happening here? So as a reminder, this is called prompted the user to enter something, or this prints out the prompt. This actually performs the prompt and reads in what is entered. And then this is moving a memory location into RDI, and this is moving a memory location into RSI. Okay. And the user has written data, no. Wait. The user inputs a string. And that string is written into the memory location defined or stored or pointed at by RSI. Now the program is reading some string into RDI, and now there's a big likelihood that this is the expected password. And it's again moving something into RSI, which is, I don't know why this statement is here again. Is it maybe wiped out after the syscall? After the syscall? Is RSI reset to 0 or something after the syscall? Because this, I would expect RSI to still remain this pointer even after the syscall. I don't know. Maybe that's the case, and therefore RSI has to be reset to this memory address. But in any case, we are setting RDI and RSI to two memory locations. And we know that this memory location right here is the string that the user inputs. And we know that this is another memory location, and those two are probably used down here in the string comparison operation, which repeats n times, exactly b times, which is hexadecimal for 11 times. So 11 characters are checked from RSI and RDI, whether they are equal. And then a flag is set, probably the 0 flag. I don't know, some flag is set that tells the program that if they are equal, we jump to the correct function, which prints out the message that the password is correct. This means ultimately that the password is located at memory location 0x402026. So this must be the password. And after that, there are a couple of other statements. There's the jump to the correct function, which prints correct to the console. Then EAX is set to 1 again. EDI is set to 1. This means that this prints yet another string, 40201F, for 7 characters, prints it out to the console, and then this is exiting the application again. All right, I think we have deciphered the application well enough. So let's have a look at what is written to the console in 40201F. And we can check that here, 40201F, and 01F should point to this last memory segment here, which is wrong. Aha, okay, so that's the wrong message. And this means that we jump if we enter the correct password to this memory location, which is 401000 or 000, which is the correct function, and then the application exits completely. So after this, there's probably no return. I don't think there's a return after this. And if there's no such jump to this function, then something is printed to the console, and that something is the wrong string, the message wrong. It's printed to the console using the syscall, and then the application exits. So if we enter the correct password right here, or rather, well, up here, but it's compared down here, and jump, then this jump happens, then if we enter the correct password, then the code down here will never be executed, because the application quits up here. That's awesome. And now we can check this memory location here, which makes the RDI pointer a point at this memory location, and then compares it with RSI, which is filled with the user input. So let's check out for 02026. And there we go. For 02026. 0, 1, 2, 3, 4, 5, 6. So that should be the starting address of the password that is expected, and it's exactly this one, super secret. So while the entire time we could basically see the password here in the plain text or even in the strings utility, it was a lot of fun to really reverse engineer and understand completely what this assembler code does at assembly level. And we learned a ton today. I don't know how I can put my gratitude in words, because you guys, you put your feedback about what I'm doing in the comments, and I'm really studying your comments. And based off your comments, I am recording new videos with already improved knowledge. And then when I'm recording the new video, I am learning new stuff on top of it again. So this is like a win-win-win-win situation. It's just awesome. It's just awesome how much growth there can be if you have a community with people and you comment stuff. You put positive comments into the comments section, and really help me improve. And also that this goes out to you, to all of you. You can also share your problems, your whatever you face in the comments, and people will help you. I'm completely sure of that. I mean, especially if you don't understand something that happened in the video. All right. But so overall, we have completely understood the disassembly of this CrackMe, which is written in pure assembler code. And we are able to crack it using the password which we retrieved. So the password is super secret, and that's a successful reverse engineering and crack. And I couldn't close this with a better result. This was an awesome episode. Thanks everybody for watching, and see you again next time. Bye.